Now we're on page 2 of section 4.4. One of the main tasks for the remainder of the course is to prove the three value theorems that you might remember from Calc 1. The extreme value theorem, the intermediate value theorem, and the mean value theorem. The first of these, the extreme value theorem, is actually a corollary of the theorem we've just proved regarding compact sets. Remember, a corollary is something that follows rather quickly from a previous result. So here's what the extreme value theorem says. If f from k to r is a continuous function on a compact set k in the real numbers, then f must attain a maximum and minimum value. In other words, there exist numbers x0 and x1 in the domain k such that if you look at the value of the function f at those 2 points, f of x0 and f of x sub 1, then f of x is always between those two, or possibly equal to them, for all x in the domain k. So let's sketch a picture of this theorem before we try to prove it. And I'll just make a little graph here. Okay, so k is a compact set. So again, I suppose I'll represent it as some closed and bounded interval, although it could be much more bizarre and interesting. There we go. And let me try and sketch a graph of a function f whose domain is more or less this interval. Now that's, not sure that's a function right at that point, but you'll bear with me. So suppose that's our graph, and then I'm going to draw some dotted lines where it looks like the maximum and minimum values of this function occur on the set k. And looks like that's where the minimum value happens and the maximum value up here. So I will call this my x sub naught here, the location of the minimum value, and then the endpoint here will be x sub 1. And so that would mean that this value here is the minimum value, f of x sub naught, and up here we have the maximum value, f of x sub 1. Okay, so with that picture in our minds, let's try to show how this theorem follows from the preservation of compact sets by continuous functions. Okay, well, since k is compact and f is continuous, the first result we get from that previous theorem is that f of k is compact. And then since f of k is compact, by Heine-Borel, it is in particular bounded. And if it's bounded, then it's bounded above, so a supremum exists. So let's call it m, which we'll define to be the supremum of f of k, exists. Well then, it follows from exercise 3.2.12 part D, which you've completed already, that the supremum m is a limit point of the set f of k. And that should make sense because, remember, m is the least upper bound. And so you have to imagine the points of f of k sort of approaching m from the left side and getting infinitely close to it. So it's a limit point. Now, the other thing that Heine-Borel gives us for this compact set f of k is that f of k is closed. And since it's closed, it contains all its limit points. In particular, it contains the limit point m. Now, for this number to be an element of f of k means that there's some element of k which maps to it. So we can say, thus there exists some x sub 1 in the set k, such that f of x sub 1 does equal this value m. Okay, well, what does that mean? M is the supremum of f of k, and by definition of the term supremum, that means that any element of f of k has to be less than or equal to this upper bound. So we have f of x, less than or equal to m, or in other words, f of x sub 1 for all x in k. Well, we can do the same thing with the infimum to obtain our x sub naught. So a similar argument with the infimum, which has an I after the f, yields the minimum value f at some point x naught in the domain. And that completes the proof.